Okay, so let's start. So, what I want to do today is two things. One is talk about the exam, and two, I want to at the end ask you to complete these ISIS forms. So my plan is to go over a few questions. I'll tell you what I thought I'll do, but I'm more open to any other questions. So I want to go over EM because, so I'm going to start going over the exam from last year. Hopefully many of you have looked at it already. If not, we'll do it today. I'm going to go over two of the problems that I thought were the hardest on EM and probabilistic models. And then do one problem that has to do with multi-class classification because there was a request to talk about multi-class classification. As I said, if you have other questions, requests, we can try to address this. So far, any? No. Okay. So let's start with this. So can you read this at the back? Okay. So here is a nice story about we positioned it in the context of neuroscience. It's actually a real example. So your brain has neurons that respond differently to whether you're viewing a cat or a dog. Each neuron reacts all the time, but reacts differently on whether it's a cat or a dog. Each neuron has a different firing rate response, which is a non-negative integer, when viewing a cat or a dog. These firing rate responses are noisy. Specifically, that can be described as a Poisson distribution centered at their mean firing rate. In this problem, we will assume that your brain uses EM as a way to learn in an unsupervised way to distinguish cat from dog. Of course, they will not know which one is a cat, which one is a dog, but it will distinguish these two observations. And it's going to do it using the noisy firing rate responses for these two neurons. Okay, so the animal you view is going to be denoted by Y, and it takes two values, cat and dog. X1 and X2 correspond to the response measured from the two neurons. As I said, non-negative integers, the values are lowercase x1, x2. Okay, so this is the model that we have. And that was still part of the problem definition. So there are 3 points, 3 variables, y, x1, x2, generated from the following probabilistic model. First of all, we generate y, so we choose what to show you. Given that, x1 and x2 are going to fire. So you have a model that looks like a small tree, y, and arrows from y to x1 and to x2. Okay, and we assume that the probability p of xi given y is the Poisson distribution, which is this. So the probability that the firing rate is k, is this lambda to the k e to the minus lambda divided by k factorial, where lambda is the parameter. So this is what defines the distribution. Okay. So given that you understand this model, you know that these are the parameters that we care about, right? So we care about the parameter, the prior for y. We're going to call it lowercase lambda, and p of y being 0 is 1 minus this. And then we care about the probability that x1 being something given that y is 1, and x1 being something given that y is 0. And the same thing here, x2. And we assume that in these cases, these are a Poisson with different parameters. Okay? Any questions on the model? So it's essentially a naive Bayes model and you know that for naive Bayes, these are the parameters that you need. You have two variables, x1 and x2, and the only difference is that your observations here will only consist of x1 and x2, and you will not know the label, which we're going to do with EM. Questions? Okay, so here is what I just said in a more formal way. You're given M examples, which are these, just pairs of xi's. Each example is two numbers, xi1, x11, x21, up to x1m, x2m, which are positive numbers. And the y variable is always omitted. So you don't know what's being viewed. The goal is to estimate the model parameters, which are these. And the way we're going to do it is with EM. Okay, so basically what we're doing here is we are guiding you through the EM algorithm, as we've done also in the problem that I've done here in class and problems that we've done in the homework. And I'm going to go over this. So again, the first thing that we want to do is we want to be able to express this joint in terms of the parameters, specifically the unknown the 5 unknown parameters. And I'm going to use here these letters just because it's going to be simpler to carry this than this. But you can choose how you want to do it. Okay, but so the first step, as I said, is always to think about P of x, P of the observations, where we omit the y. But what we are doing as a way to compute it, we basically marginalize. So the probability of x1, x2 is the probability of x1, x2 and y being 1, plus the probability when it's 0. Nothing new here, hopefully. Okay? And now I can write these joints as a function of the parameters, given that I know the model. Given that I know the model, the probability of x1, x2, y is the probability of y times the probability of x given y, x1 given y times the probability of x2 given y. And I'm doing it here for y equal 1, and I'm doing it here for y equals 0. And this is just putting the names, the notation that I used before. Questions? No questions. Okay, so now the first step of EM is our guess for the label. So what is the probability of y is equal to 1 in this case, right? That's the first thing we're doing. So I'm denoting Pij, the probability that yj is equal to I, given the x1, x2. So j is my example. And for each example, I want to know what's the probability once I observed x1, x2 that the label is I. Well, I here ranges from cat to dog. So that's the probability that the hidden variable y has the value I, given the observation. And we can write it down. So P1, which is the probability that y is being 1, I'm not reading the j here. The j will just carry because the same thing holds for each one of them examples. So I'm just going to read everything without the j. So P1 is the probability of y being 1 given x1, x2. Bayes rule, it's the joint P of x1, x2 and y being 1 divided by P of x1, x2. And we actually know how to write it down. All right? So basically what I have here, again, using the assumption on the model, it's exactly the same step that I did here. I can write it as P of y being 1, which is this gamma, P of x be 1 given that y is 1, P of x2 given that y is 1, right? Which is exactly this term. Okay? What's written here and what's written here is the same thing. Okay? And then I normalize. This is exactly what we derived in the step before. Questions? Okay, so far it's standard. Now, the next step is we need to write the expected log likelihood. So here we took some shortcuts. So let me just write this in a, let's see. Can you read this? Okay, so what do we have here? So let's see if this works. Okay, so I'm starting here by writing the likelihood. What is the likelihood? I have m examples. So the likelihood, and the examples are assumed to be independent. So the likelihood is the product over all m examples of this joint, p of x1, x2, y. I'm omitting the j here, but there is a superscript j on each one of these letters. Now, the log likelihood, I'm taking log for this, so it's the sum, 1 to m, log of this joint. And in EM, what we are doing is we are doing the expected log likelihood, expectation relative to the missing variable, the y. So I should have written here small subscript e relative to y of the log likelihood, which is the expectation of this sum that I've written here. Sum 1 to n of p, which is, log p. Sum 1 to n, here it should be log p. Equal sum 1 to m, expectation according to y. I should have written here also according to y. And I can do here also to clarify this according to y. So at the end I have sum 1 to m. This is for the examples. Expectation according to y, log p. Okay? So what does this mean? I'm keeping the sum here. I'm writing it a little bit more explicitly. Expectation relative to the variable y of this random variable, log of this joint. Okay? And now we can write this more explicitly. So sum, I'm copying the sum here. What is the expectation of the random variable? It's the probability it takes a value times the value summing over this. In this case, there are two possible values for y. So E1 is the probability that y is being 1. That's what we derived the previous section, times the value of the random variable, where y is 1, where I substitute y equal 1, plus P0 times the value of the random variables, where I substituted y equals 0. Okay, so this is just making this expectation explicit. Making it a little bit more explicit, still I have the sum. And now, inside the parentheses, I have my gamma, which is P1, log. I'm just taking the joint and I'm writing it using the assumption on the model. So what is the joint? It's P of y being 1. Yeah, you can read this. P of y being 1, P of x given y being 1, should have been x1 here. P of x2 given that y is 1. And the same thing here. 1 minus gamma log P of y being 0, x1 given that y is 0, and x2 given that y is 0. Okay, so really no magic. And I think at this point we can join what's written here, which is just that. So again, I have sum over all the examples, this component, and then inside I have the expectation, which is P log of the random variables, P log of the random variables, P0 and P1. And now we can substitute the Poisson distribution. So again, what do I have to do? I have P0 is here, just like here. And then I have the case of 0 is the product of 1 minus gamma, the probability of with x1, and the probability with x2. So one term is with alpha 0 and x1, another one is with beta 0 and with x2. And the same thing is going to be here with alpha 1, beta 1, and with the other x. So that's it. That's the expression that we get. And now taking log for this, if you want. Questions? Okay. So the next, so basically, we wrote the expected complete data log likelihood expression in terms of the unknown parameters and the PIs, kind of the fractional labels. Yes? The way we write it, actually, is we write it this way, because I want my random variable to be the log of this. So the way I've derived this, if you remember, shows that this is really what we need to do. Yeah. So I've it's a different thing. Here we wrote the join this way, right? And that's what you get, right? Basically marginalizing, right? When we write the log likelihood, we write it this way, where here the p's come from the fact that it's expectation. So there are two ways to interpret it. I mean, it's also possible to start with what you said as a starting point, and basically either way we're making some leap here because we don't know how to compute this, right? So it depends on how you want to explain what you're doing. One way to explain what you're doing is the way I'm doing it here. Another one is to start just with this, this. And then you will not be able to explain it as an expectation of. It will be some kind of an upper bound because I'm actually not doing really expectation. So it's really more semantics. How do we explain this? But really, that's what we want to do. We want to think about the likelihood this way when we do the expected log likelihood. It boils down to the same thing. Okay, so this is so far relatively standard. I think that the key step where people had difficulties was in fact this one, because you forgot your calculus 1. So I'm going to remind you. So basically, once we have an expression here or here, you can choose whatever you want, either this expression or you can start directly with this expression. We have to differentiate it. And we have to differentiate it relative to the parameters that we care about. So what we've shown here is how to do it relative to gamma, which is the easiest. And then I'm going to show how to do it relative to alpha 1. So with respect to gamma, the key thing that you observe is that this disappears. And all this disappears also, all this second part here. So what you end up with is sum, differentiate this part, and differentiate this part, right? Which, given that you know that the derivative of the log is 1 over, log x is 1 over x, it's easy to see that that's what you're going to get. So you get negative because of this guy, p0 over 1 minus gamma plus p1 over gamma. And the sum over all m of this has to be 0. That's the easy part. This one is a little bit more involved, and actually I've written it here just to make sure that, what's it? Yeah. See? Yeah, it's readable. So I've taken a few shortcuts, but again, should be easy. So I want to differentiate relative to alpha. What I have is a sum pj log of this expression. Notice that that's the only thing I have because everything else disappears. When I differentiate relative to alpha, the term that does not have alpha disappears. I do have this denominator here, xj factorial. I omitted the index of the alpha, so the same thing is going to be for alpha 0 or alpha 1. So the first thing to observe, if you're doing it this way, is that the denominator disappears. Why does it disappear? Because you have log of something minus log of this. Right? There's no alpha in the minus log of this, so it disappears. Okay, so that's one thing to observe. Again, you've seen this hopefully many times. So I eliminated the denominator. What I have is this. I have sum pj. In the denominator now I have log of something. So I'm using the chain rule, which means that in the denominator I have this something, alpha to the power of xj times alpha e to the minus alpha. And in the numerator, I have the chain rule of differentiating this expression. And this is what you get when you differentiate this expression with the chain rule. You get xj alpha to the xj minus 1. It's from this expression, times this guy. Should have been e to the minus alpha here. And then, so this is the first part, and then I have negative, and the negative comes from the negative power of the e here, minus, again, alpha to the xj, e to the minus alpha. Okay? So now the thing to notice is that every time in all these three expressions, 1 minus something divided by something, you have alpha to the xj minus 1 e to the alpha, e to the negative alpha. Right? So here you have alpha to the xj minus 1. Here you have alpha to the xj. Here you have alpha to the xj. So I can divide everything, numerator and denominator, by alpha to the xj minus 1, which means from this part, I'm left with xj. Sorry. From this part, I'm left with xj, this guy. From this time, I'm left with the alpha because I had alpha to the xj minus 1 that I eliminated. And in the denominator, I also have alpha. So the thing to correct here, that this should have been negative alpha. Okay, and that brings me to what's written here, which is the sum p. I'm bringing again here the indices, the subscript p1 to the j, xj divided by alpha minus 1. Right? This is what we showed here. Right? xj minus alpha divided by alpha. So it's a little bit of calculus 1. And if you want the sum to be 0, it's easy to see that that's the expression you get. Okay, so really shouldn't be that difficult once you know the steps that you have to do in order to run EM. And it's the same thing every time. The only thing that is going to be different between one model and another is how you write these expressions. This is where the assumptions of the model come into play, right? The fact that I can write this joint as P of y times P of x given x1 given y times P of x2 given y. Had I given you a different model, this decomposition would have been different. So that's one difference. The other difference is when you plug things here, right? Because the probability of x given y, in this case it's Poisson, some other cases that you've done is something else. And also notice that in this case, the derivatives were very easy. And you can do it for all 5 parameters. They are completely independent. That's a little bit different than what you had in problem set 6 and also in problem set 7, where the parameters are dependent. So it's a constraint optimization rather than unconstrained optimization that I do here. But we gave you saw the solution for problem 6, so you should be able to know if you haven't, if you did not remember how to do it. Questions? Yeah. Yeah.
How did you get rid of the pieces?
I did not get rid of P sub 0. It's here. Oh, this. Let's see. Yeah, you're right. Yeah. P0.
Plus P1
Yeah.
So you have to apply that constraint.
No, here I'm not. These are just numbers, right? So it's just algebra. So this is the term that I got, and then I isolate alpha, and I can gamma, and I can write gamma as a function of P1 and P0, or if I want, just as a function of P1, when I substitute P0 is 1 minus P1. So it's not the same constraint that you have, say, in the homework, where the parameters that you compute are constrained. Here, P0 and P1 are just numbers. You already know them from the previous round.
Right. But in the second one, we solve for...
Well, the thing is, look at this formula, right? So here, when you differentiate relative to gamma, this 2 disappears, and this 2 disappears, but you still have these 2 things. So you have P0 and P1. On the other hand, when you differentiate relative to alpha, let's say you differentiate relative to this alpha 1, all of this disappears, and you just remain with this guy. Right? So, other questions? Okay. So here is the second question that I wanted to talk about, a little bit about probabilistic representations. So I don't even need to address everything here, but we gave you 2 models. Given that it's an exam and there isn't a lot of time, don't expect to see big models unless the computations are very easy. Really, you cannot do EM on something that is larger than these many variables, given the time. But anyhow, in this case, it wasn't EM. We just gave you 2 models. Here are the models. One of them is a chain model. I'm going to describe it as a generative process. You generate C. Given that, you generate B. Given that, you generate A. That's one. In M2, you first generate A and B, and you generate C given pairs ABs. Okay, that's this M2. And we ask you what are the parameters that you have to compute, to estimate in order to completely define the model. By completely define the model, I mean to be able to compute the joint probability distribution. So we gave you a lot of parameters, but let's just look at this and say, what do I need? How do I write the joint here? So P of C times P of B given C times P of A given B, right? And I didn't, so if you look here, we gave you this somewhere. So it's 9, P of B given C, 6, and P of A given B, 2, I think. What's going to happen for M2? What do I need for M2? M2. What parameters do I need? Yeah. Right. So P of A, because there's no arrow leading to it. P of B, same reason. And P of C given AB. So, so let's see. So P of A, P of B, and P of C given A and B. So if it's Boolean, this conditional probability table is going to have 4 values. P of C being 1 given the 4 values of A and B, 0, 0, 0, 1, 1, 0, 1, 1, and the 1 minus this, which is P of C being 1 given the same 4 numbers. 8 numbers, only 4 of them are independent. Okay? Okay, so that's, now we ask you to do some estimation. I'm not going to do this. This is just simple counting. What I want to dwell on is, again, this is computing the probability distribution for model M1 and for model M2. It's written here. Unless there's a question, I'm going to skip that. I want to talk about this. Consider now a third model. The third model also it's a chain from A to B to C. And I'm asking which of M1 or M2 can represent exactly the same probability distribution as M3. What do I mean? What does it mean to represent exactly the same probability distribution? So P of A, comma B, comma C, when I'm writing it down relative to this model, and when I'm writing it down relative to any of the other models, should be the same. That's what I mean by represent the same probability distribution. Okay? And it turns out that it's really very, very simple to do. And I'm writing here the details of the solution. So, so M3, let's just move this so you see M3. Yeah, now you can see M3. So M3, I can write the join as P of A times P of B given A times B of C given A. For M1, let me remind you, M1 was a chain C leading to B leading to A. So where is it? So C times P of B given C times P of A given B. And the way to derive that they're the same is very simple. So I'm starting with M3, which is this, and I'm going to use Bayes' rule. So I'm leaving PA here as is. Instead of P of B given A, I know that I want P of A given B in my answer. So I can write P of B given A as P of A given B times B of B divided by P of A. I have PC given B, and I know that in my answer I want P B given C. So again, I'm using Bayes' rule for this. I'm writing it as P of B given C, P of C divided by P of B. And that's it. So the P of B here disappears because of this guy. The P of, where is it? The P of A also should disappear. Oh, P of A here disappears with this P of A. And then I get exactly what I needed for M1. So it's very simple application of Bayes' rule. Now, notice that every time you will have to estimate different numbers from the data, right? If you write it as M3, you'll have to estimate these numbers. If you write it as M1, you'll have to estimate these numbers. But still, it's the same model. Okay? Questions on this? Yeah. Question D. Yeah. D. Okay, what does this mean? Yeah. So what we did is we gave you a few examples, right? You have to write the probability of each one of the examples given the model and multiply it because the examples are assumed to be independent. Yeah. Under the assumption of M1, right? So M1, you know how to write a joint. Say it again. The probability of the model given the data, right? So how do we compute the probability of a model given the data? We use Bayes' rule, but it's the same thing that we've been doing every time when we did, for example, the tree learning, right? We compute the probability of that. We want to find the most likely tree, P of T, given the data, and we use Bayes' rule in order to do it. But basically, we already asked you here to compute everything that you need in order to do it. It's essentially a substitution. Here, let's look at M1. As we said, for M1, you need P of C, P of B given A, P of A given B. Okay, so here we didn't ask you to compute exactly the numbers that you need for M1. You need to compute a little bit more for M1. But basically, you have to compute these three families of parameters, and now you can compute the probability of the data given M1, and from this you'll derive the probability of M1 given the data. Okay? Questions on this? Yeah. Yeah. No, it's not one. It's the probability of the data. In most cases, you don't need to compute it. Exactly. Yeah. So notice that it depends where what is the question. Often you don't need to compute the denominator. You can just normalize if needed, or not, if all you do is argmax. But let's look here. We actually did it earlier today. Here I actually computed Right? So this is the probability of the data. Right? It's not 1, it's something. Okay, questions on this? Okay, the next thing I wanted to do is to look at a multi-class classification problem. So this is from an exam in 2011. So here's the problem. Okay. You basically, the setting, the story is a context-sensitive spelling correction. So you have interns that make mistakes using appropriate prepositions. And you think about this as a problem of identifying which of the 4 prepositions should be mentioned, written, used in a context of a given sentence, right? So you know there has to be a preposition there, and you want to know which one. So there are 25 examples for each, and you want to build a classifier that predicts that. Okay? And what we are going to do here is we're going to look at 2 different classifiers and ask some questions on how do we set up the multi-class classification in both cases, and what are the differences. And you'll see actually that there are interesting differences if you haven't thought about it before. Okay, so what are we doing? You decide to use 1 versus all. You should all know what that means. But you're not sure which classifier to use, perceptron or naive Bayes. So we're going to complete the table here, or you will help me to complete the table here. Question 1. I have a training protocol, and I'm training this and this. For perceptron, what I need to decide is what are the positive examples and what are the negative examples. What do I write there? If the positive, I need to know the labels. So I'm assuming that you're going to put here each one of the 4 labels as positive examples. The options are with, on, for, and at. Let's assume that I have here with. The label is going to be with. How many examples? How many positive examples will I have? How many positive examples for with? 25. How many negative examples for with? 75. So that's the key question here, really. To realize that 1 versus all means that you choose 1 label as the positive, all the rest as the negative. So here you will have to write, if this is with, the labels are going to be the other 3, 75, and you do the same for all 4. So that's easy. What about naive Bayes? In naive Bayes, we have to compute parameters. What are the parameters that we have to compute? So P of each label, and you know what that is going to be. What's going to be P of each label? A 4th. And then we need to the probability of each variable given y, which we are giving you here. Right? So it should be this guy. Right? So it's 17 and 19. Okay. Next thing is, so we already trained the model. Now what are we doing in order to test? I'm giving you an example. What are you doing on this side? How will you label an unseen example based on the classifier you learned above? Here comes an example. What do you do? Notice that what you learned before, you actually learned 4 classifiers, right? P of with, P of on, P of, the 4 prepositions that you had. What are you doing with them? Yeah? Right, so you evaluate each one of them on the example and you do argmax. What are you doing here in naive Bayes? Yeah? Probability of y being with given the data, which at the end is going to boil down to multiplying the appropriate, each one of the 4 things here. For each, again, you're going to do it 4 times. You're going to compute P of y equal with, P of y being on, P of y being each one of the 4 values, times, in each case, the appropriate product of these. And again, you're going to do argmax on 4. So in each case, you are evaluating 4 classifiers, only that you evaluate in a somewhat different way. And then you do argmax. So essentially, no difference so far. Okay. Now, after you train the model, you realize that the model isn't good enough. You notice that there's another common mistake with the preposition in. You collect 25 more examples where the correct preposition is in, and you want to learn a classifier that distinguishes 5 classes instead of 4. And now the question that we ask is, how do we modify the existing classifiers that we have in order to now get a 5-value multi-class classifier, as opposed to the 4 that we had before? Okay, so do you have to change the perceptron classifier you learned in part 1? Yes. Otherwise, it wouldn't be interesting, because, I mean, the classifier that you learned before will never predict in. You have to do something. Okay, so now I want to know, in the case of naive Bayes, what else do I need to, what do I need to do now? What do I need to, what parameters do you need in order to learn the new classifier? Yeah? Okay, so if we look at the parameters here, we need again, as we said, the P of y. What is P of in now? Now it's 1/5. We have 125 examples, 25 of them. What happens to P of with? We need to change, right? Because before it was 1/4, now it goes down to 1/5. So we need to change the priors. What about 17? We said that we're going to, for each label y, we need P of xi given y. So first of all, we have to do this for the new one, in, which we didn't have before. We have these 25 examples on which we're going to compute this, right? Because these are the only 25 examples for which the y equal in. What happens to the example of with? Right? We don't need to change this probability distribution because they are completely independent of the other labels. Okay, so that we actually answered what parameters do you need to, in order to learn the new classifier? What parameters from part 1 can you reuse And as we said, most of the parameters, the P of xi given the 4 y's that we had before, they stay the same. You don't need to re-estimate them. And what are the new values of the parameters from part 1 that you have to re-estimate? We talked about it. The priors have to be re-estimated. Okay, I think we addressed everything. Okay, so what happens on the left side? What are we doing on the left side? So we solved the right side, the naive Bayes thing, and what we said is that essentially we have to learn P of in, or the classifier for in, P of in and the conditional probability given in, and we really don't need to touch the 4 classifiers from before. All we have to do is change the prior. What happens with the perceptron? Right, so now we place the 25 examples. There's no other way. And we have to relearn. Right, so now we're going to learn 5 classifiers. But if you think about the with classifier from before and the with classifier now, it's not the same classifier. Before, the with classifier was trained on 25 examples of with as positives and 75 or negative. Now it's going to be trained on 25 examples of with as positive and 100 negative examples. Different classifier. And there's no other way. You just have to retrain it. So how will the test protocol change? Won't change. Okay. It's the same thing, only that now you have 5 classifiers that we generated as we explained. That's it. But I think it's kind of interesting to realize, if you haven't realized this before, that actually there are differences depending on the type of classifier. And the reason is that in naive Bayes, everything is independent. All the other classifiers, you could have placed SVM instead of perceptron here. If you do the one versus all, you have to retrain. Questions? No more questions. Any other part of any topic that we talked about that you want to discuss? Okay, so just to remind you, be here a few minutes before the exam starts next Tuesday. Closed books, covering most of the material of the year with an emphasis on the second part after the midterm. Okay, so here's what I want to do now. I want to give you the evaluation. I don't know how many of you have done it. I think this will be enough. So I need to read something to you. So I'm going to first distribute these. You have to use pencils. So I'm going to distribute pencils also. I need a volunteer that will take everything and return it. Volunteer? Could you send this up? Oh, you're right, thanks. The volunteer will have the hard job of collecting everything, putting this in the envelope, and putting it either in a university mailbox, because it already says return to, or giving it back to my assistant. And they will also have to collect the pencils. That's even more important. Collect the pencils and give it back to my assistant. Volunteer. I'm going to volunteer. Okay, thanks. So let me read it to you, because the purpose of this instructor and course evaluation system questionnaire is to provide me with the evaluative information based on your perception of the course. The result will not be sent to me until after the final grades are reported, and in fact, a couple of months after, so don't worry. Your complete cooperation is appreciated, and that's true. So two key things that you need to know has to be with a pencil, 3 things. 2, you don't need to complete the demographic item number 5, student sex. And what's really important is 2 things. Please answer questions 1 and 2, because these are really the key questions that they use to evaluate the class, so don't skip 1 and 2. And once you're done with all the questions, please turn it to the other side. That's important, because there are questions there, and I'd appreciate if you write something in each one of them, because I'm going to read it. Everyone has a form? I think you're too busy. Once you're done, please bring it here.